Alright, hi everyone, welcome back. So in our previous video we just did an intro to what the modulus was and how we calculate easy questions. In this video we're going to talk about some slightly harder ones and we'll go through an exam style question as well. So just a reminder, our modulus is taken directly from Pythagoras' theorem, and so in our last video we talked about the fact that it's the square root of x squared plus y squared. So we're going to be using this formula still. So let's get straight into it. Let's look at a harder style question. So what if we're asked to find the modulus of 2 plus I over 3 plus 2i? Now, very, very important from our last video, we like to draw what the complex number looked like. We like to draw on the complex plane. Now, we don't have to draw it. Once we've kind of got the formula down, we realize it's just the square root of the real stuff plus the imaginary stuff, all squared and square rooted. And when we look at a question like this, it is not obvious initially what is real and what is imaginary. Now, to calculate the modulus, we must separate the real and imaginary. So that is what we must do. If it's not clear what's real and what's imaginary, that is our first job. So a very, very typical type of exam question or something is where they give it to you in fraction form, and our default to separate real and imaginary is to multiply top and bottom by conjugate. So that's going to be my first step. Before I do the modulus, I'm just going to try and separate the real from the imaginary of this number. And to do that, I'm going to times top and bottom by the conjugate of the bottom. So we're just going to go through the process of expanding this out. We end up with 6 minus 4i plus 3i minus 2i squared, which is going to be plus 2. That's my last two things multiplied together. I got this from minus 2i squared, just in case you were wondering. And on the bottom, we're hoping that all the i's will cancel out. That is the purpose of multiplying by the conjugate. We end up with 9. We have got minus 6i, we've got plus 6i, and we have got minus 4i squared, which in this case I'm going to write as plus 4. Similarly to this one up here, it was minus 4i squared. And when we simplify this a little bit, we end up with 8 minus I on the top, and my middle two terms, the minus 6i and the plus 6i, will cancel, and I end up with 13 on the bottom. And now I can separate these into two parts and have 8 over 13 minus 1 over 13i. Happy with that? We've separated the real and the imaginary. Now, it's very similar to a question we did before. This is an ugly number to try and draw, but you could imagine that it will end up being a triangle, with one side being 8 over 13 and the other side being positive 1 over 13, even though I've gone down. Like if we just do a real rough sketch of what this is, I've gone across 8 over 13, wherever that is, it's less than 1, and down 1 over 13. So we're somewhere here, across and then down. But if I draw my triangle and I draw it out again, it's just a triangle where one of the lengths is 8 over 13. I've drawn it terribly inaccurate, but that's fine. And 1 over 13, obviously 8 over 13 is bigger than 1 over 13, but nevertheless, it's a triangle. We can do Pythagoras' theorem to figure out r. So now if I'm trying to do the modulus of this question, which is what we are trying to do, this would be the square root of the real stuff squared, which is 8 over 13 squared, plus the imaginary stuff squared, which is 1 over 13. And whatever that is, I mean, I can't really be bothered calculating that, but you can put that straight into your calculator and that will be your modulus, that will be your answer. Let's leave it there. I don't really care. It's going to be an ugly decimal. It's not nice, but our calculator will do the rest of the work for that question. So, classic style question, we must do conjugate to separate real and imaginary. Once we have real and imaginary, if you like to draw the triangle, really you want to practice this enough that you don't have to draw the triangle. It's just the real stuff squared and the imaginary stuff, but we don't care about negatives. Negatives just means I'm going down, but when I draw that triangle, I only care about the length, so I just care about how long is that length and how long is that length. Don't care about negatives, so it's just the positive of that. Even if I put the negative there, squaring it's going to make it positive anyway, and then I square root it. Whatever that is, I don't even know. I haven't done it. Calculator will do it. Let's do another type of question. All right, another classic style of question is when we're trying to find the modulus of z and some extra stuff that's happened. So I'm gonna show you the long way to get this, and maybe I'll confuse you, maybe I won't. There is a very easy way to do this, but I want to show you why it works. So again, we're going to try to draw a picture. All right. I'm sorry, I'm going to make that a plus. It just makes the picture easier to view. I'm sorry. It can be a minus, so the picture's just going to be a little bit uglier. So let's draw a picture of what this will look like. We'll go over here. Alrighty. Now, to make my picture easier for you to understand, I always pick Z in the positive, but it technically can work anywhere. It just helps our brain if we pick one up here. So I'm just going to let Z, let's say, be here. And remember, Z is X plus IY. So that's my Z. Right there, X plus IY. So that's this Z here. Now Z has been added 3, and it's also been added 4I. So we can imagine, this is my complex number, I'm adding 3 real. So imagine this was like 2 plus 5I. If I added 3, I'd be adding 3 onto the 2, the real part. So it's gone to the right by 3. So if I imagine this is where X is, X plus 3 is like over here somewhere. So this is over here, X plus 3. And similarly, if I added 4I, let's say that was whatever I just said, 5I. If I'm adding 4I, it's going to be 9I. So we are going up. So if this is my Y over here, I'm going up by 4. Y plus 4. And so my new complex number is here somewhere. It's the old one, Z, with a plus 3. Oh gosh, I just looked at where that actually is. Sorry. It's over here somewhere, not that one. That's ugly. All right. So that's my new one. This is Z plus 3 plus 4I. And again, I'm just drawing a right-angled triangle with this. So I'm connecting that to my origin. I'm drawing it down here, and I just need my length. So if I draw this triangle separate out of here, all this length across here is it's that full distance of X across 3 more. So this distance is X plus 3. My distance going up here is that whole distance of Y plus another 4. So this is Y plus 4, and I'm still trying to calculate the distance from the origin R. And so Pythagoras' theorem, it's just a tiny bit harder now because it's not just a length, it's a thing, it's a sum of 2 things. So we're just going to write R squared is equal to this side squared, be careful to put it in a bracket, plus the other side squared. And in actual fact, all I need to do now is square root that. Now, for most purposes, you can just leave it exactly like that. There's no point expanding all of that out. Now, usually these questions show up with something else. They might equal something, so you're trying to equal that. You might have to square both sides to get rid of a square root. Rah-de-rah-de-rah. There is the common question. So this is my final answer. That's done. We're finished now. There's a common question that many people say, we've got a square root, we've got 2 things being squared. Does that cancel? Does the square root and the squared cancel with each other? And in this case, no, it does not. I'll show you 2 examples of why. So let's think of something where we have a square root, and let's say we had 3 squared here plus 2 squared. So the similar question is, we've got a squared, we've got a squared, we've got a square root. Does that cancel? The question is this just 3 plus 2? Is it? We'll put a question mark here. Is that? Can I cancel the square root and the squared and just write 3 plus 2? Well, we can easily show that it's not. All I have to do is square 3 and square 2 and add them together. It's 9 plus 4. So this is actually the square root of 13. Does the square root of 13 equal to 3 plus 2? No, it definitely does not. The problem here is this plus, which is this plus here. It means it gets a little bit more complicated than the square root and the squared cancelling. It is true that the square root of x plus 3 squared, it is true that that square root and that squared will cancel, and we'll just get x plus 3. But as soon as we have this addition of another thing, we actually lose the property of that square root cancelling with the squared. All right, so if we just compare this with this real quick, there is an easier way to do it than drawing this picture every single time. I don't really want you to draw this complicated picture every single time. So the rule is that if you have a modulus with like a z and some extra stuff added on, we're going to first imagine that z is x plus iy, and we're going to have that plus 3 and that plus 4i. And really, when we do the modulus, a better way to think about it is the square root of the real squared plus the imaginary squared. So then if you look down to my answer, the real stuff is the x and the 3. Here they are, the x and the 3. They have no i's, so it's the real squared. and it is the imaginary squared, but we do not include the I. So the imaginary with the y and the 4, and there's my y and my 4, and they are being squared. So it's the square root of the real squared plus the imaginary squared, and that is a very good way to think about it. Let's try one more real quick just to see if we've locked that in. So if I wanted to know the modulus of z plus 6, I'm going to rewrite this as x plus iy plus 6 modulus. And with what we just said, this will equal to the square root of the real squared. In this case, it's the x and the 6, plus the imaginary squared, which in this case is just y. And that would be my final answer done. All right, let's try one more example. This video is going a little bit longer than I hoped, but that's all right. I wanted to explain it in depth. And this example is a complicated one, so we'll go for a little bit. This is taken straight out of the 2020 NCEA New Zealand exam for complex numbers. It says, for complex numbers u and v, prove that if u plus v modulus is equal to the modulus of u minus v, then u divided by v is purely imaginary. I apologize, I'm going to run away for 4 seconds and turn my light back on. My stupid lights are automatic and they turned off all by themselves. All right, let's get through it. So, an issue here is we have u and v, and usually I've been using x plus iy, but I can't use x plus iy for both of them because they're different, we're assuming. So we're going to use u is equal to a plus bi, and we're going to use v. Really, we just want 2 different letters. You could use c plus di, we could use x plus yi for this, doesn't really matter. Let's do c plus di. Those are my 2 complex numbers, u and v. We need to prove that the modulus of them added is equal to, or if the modulus of them added is equal to the modulus of them subtracted, then them divided is purely imaginary. Let's have a look at this. Let's first just work with this for a bit. We'll get to that second part soon. So modulus is going to be a plus bi plus c plus di, and that is equal to a plus bi. Be careful here, we're minusing all of v, so we're minusing c and we're minusing di, not just minus c plus di. All right, now according to my examples just before that, we want to write this as the real stuff squared plus the imaginary stuff squared, all square rooted. So that's going to be a plus c squared plus b plus d squared, all square rooted. And they're telling me that that is equal to a minus c squared plus b minus d squared, all square rooted. So my first step right here, because this side is square rooted and this side is square rooted, I can square both sides. So I've got, I'm actually going to, so let's write it out. A plus c squared plus b plus d squared is equal to a minus c squared plus b minus d squared. Now I'm going to expand all of this out real quick. So I'm going to end up with a squared plus 2ac plus c squared plus b squared plus 2bd plus b squared is equal to a squared minus 2ac plus c squared plus b squared minus 2bd plus d squared. If you don't trust me, write the brackets out as 2, expand the whole thing, you should get exactly what I've got here. Now a whole bunch of stuff is going to cancel. Essentially, I'm going to minus a squared from both sides and it's going to be gone. I'm going to minus c squared from both sides, they're going to be gone. I'm going to minus b squared from both sides, they're going to be gone. And I'm going to minus, this is supposed to be a d, I apologize, that was a typo. I'm going to minus d squared from both sides, we're going to be gone. And to tidy this up a tiny bit, I mean, let's just write it as 4ac plus 4bd is equal to 0. All I've done here is I've added my 2ac over here and got 4ac, added my 2bd over here to get 4bd, and perhaps, who knows, let's just hold on to this for a second now. All right, so they've said, prove that if this is true, which boiled down to basically this being true. If this is true, and I worked through it and it boiled down to this, we now want to show that u divided by v is purely imaginary. If this property is true about u and v, we need u divided by v. We need to prove that this is purely imaginary. So now we're going to work with u divided by v. using the letters or what we chose at the start, this a plus bi. So this is going to be a plus bi divided by c plus di. Now similarly, if we've got a complex number that's being divided and we're trying to talk about real and imaginary things, we must be able to separate this into real and imaginary, and the common overriding theme is to multiply top and bottom by conjugate. So we're going to go straight ahead and do that. C minus di top and bottom. C minus di, we'll expand that out. We get AC minus ADI plus BCI, and then I get a minus BDI squared, which is going to be a plus BD. And we are dividing that by C times C, which is C squared. The middle stuff's going to cancel. I already know I've done enough conjugates to know that middle stuff's going to cancel. And then I end up with minus D squared I squared, which again becomes plus D squared. So we want to break this into its real and its imaginary parts. The bottom, there's no i's, which is great. And I can break this into the real, which is going to be AC plus BD divided by C squared plus D squared plus BC minus AD over C squared plus D squared, and that's got an I with it. So I took the real, the AC, and the BD. Here's my real, and it's over the bottom, and it's plus the imaginary. I just put this one in front for some reason because it was positive. That one was minus. I put it at the back. They've both got an I. Here it is, real, imaginary. I can merge them back to go here because they've got the same denominator. It would go straight back to here. Now they've said that if this is true, which we boiled down to here, then we need to show that this is purely imaginary. Now this is purely imaginary. Here's the imaginary. It's got this real stuff. Essentially, we're trying to show that this is nothing. This is zero. We want this to be gone so that we just end up with this imaginary thing over here. So that's our job now. We need to somehow use this box to show that this is zero. Now, luckily with this box, I can do one thing. I can divide both sides by 4. If I divide by 4, I end up with AC plus BD equals 0. And lo and behold, we look over here and we've got our AC plus BD. So really what that is saying is that this is now 0 over C squared plus D squared, which is still that, plus BC minus AD over C squared plus D squared, and this is I. That's my I. This whole thing is my I term. 0 plus that means it's only I, which means it's purely imaginary. All right, hopefully this video was helpful. We went through some slightly harder questions to do with the modulus. If you take anything away from this lesson, anything at all, it is that the modulus of Z and any extra complicated stuff, A plus CI or whatever, it's going to be the square root of the real squared plus the imaginary squared. Very, very important. You should have that locked in your brain forevermore. That's what the modulus is equal to. In this particular case, it would be the square root of x plus a squared plus y plus c squared. All right, hopefully you like this. Please like and subscribe and tell all your friends and blow my channel up. Let's go all the way to the moon. No, I'm just joking. These are the only 2 videos we got. Hopefully I'll make some more. If there's anything you really would like me to make a video explaining or helping, I am open to that. So leave a comment. Let me know what you want me to make videos explaining. And thanks for watching. See you guys later.